Hey, I'm Mandy from DEEPLIZARD. In this episode, we'll demonstrate how to build a convolutional neural network and then train it on images of cats and dogs using TensorFlow's integrated Keras API. We'll be continuing to work with the cat and dog image data that we created in the last episode, so make sure you still have all of that in place, as well as the imports that we brought in the last episode as well, as we'll be making use of those imports over the next several videos of working with CNNs. So to create our first CNN, we will be making use of the Keras sequential model. And recall, we introduced this model in an earlier episode when we were working with just plain, simple numerical data, but we'll continue to work with this model here with our first CNN. So the first layer to this model that we pass is a conv2D layer. So this is just our standard convolutional layer that will accept image data. And to this layer, we're arbitrarily setting the filter value equal to 32. So this first convolutional layer will have 32 filters with a kernel size of 3 by 3. So the choice of 32 is pretty arbitrary, but the kernel size of 3 by 3 is a very common choice for image data. Now, this first conv2D layer will be followed by the popular ReLU activation function, and we are specifying padding equals same here. And this just means that our images will have 0 padding the outside so that the dimensionality of the images aren't reduced after the convolution operations. So lastly, for our first layer only, we specify the input shape of the data. And recall, we touched on this parameter previously. You can think of this as kind of creating an implicit input layer for our model. This conv2D is actually our first hidden layer. The input layer is made up of the input data itself, and so we just need to tell the model the shape of the input data, which in our case is going to be 224 by 224. Recall, we saw that we were setting that target size parameter to 224 by 224 whenever we created our valid test and train directory iterators. We said that we wanted our images to be of this height and width. And then this 3 here is regarding the color channels. Since these images are in RGB format, we have 3 color channels. So we specified this input shape. So then we follow our first convolutional layer with a max pooling layer where we're setting our pool size to 2 by 2 and our strides by 2. And if you are familiar with max pooling, then you know this is going to cut our image dimensions in half. So if you need to know more about max pooling or you just need a refresher, same thing with padding here for 0 padding, activation functions, anything like that, then be sure to check those episodes out in the corresponding Deep Learning Fundamentals course on DEEPLIZARD.com. So after this max pooling layer, we're then adding another convolutional layer that looks pretty much exactly the same as the first one, except for we're not including the input shape parameter since we only specify that for our first hidden layer. And we are specifying the filters to be 64 here instead of 32. So 64 is, again, an arbitrary choice. I just chose that number here, but the general rule of increasing functions as you go into later layers of the network is common practice. We then follow this second convolutional layer with another max pooling layer identical to the first one. Then we flatten all of this into a one-dimensional tensor before passing it to our dense output layer, which only has 2 nodes corresponding to cat and dog, and our output layer is being followed by the softmax activation function, which, as you know, is going to give us probabilities for each corresponding output from the model. All right, so if we run this, we can then check out the summary of our model, and this is what we have, exactly what we built, along with some additional details about the learnable parameters and the output shape of the network. So these are things that are also covered in the Deep Learning Fundamentals course as well, if you want to check out more information about learnable parameters and such. So now that our model is built, we can prepare it for training by calling model.compile, which again we have already used in a previous episode when we were just training on numerical data. But as you will see here, it looks pretty much the same as before. We are setting our optimizer equal to the atom optimizer with a learning rate of 0.0001, and we are using categorical cross entropy, and we are looking at the accuracy as our metrics to be able to judge the model performance. Just a quick note before moving on, we are using categorical cross entropy, but since we have just two outputs from our model, either cat or dog, then it is possible to instead use binary cross entropy. And if we did that, then we would need to just have one single output node from our model instead of two. And then rather than following our output layer with the softmax activation function, we would need to follow it with sigmoid. And both of these approaches, using categorical cross-entropy loss with the setup that we have here, or using binary cross-entropy loss with the setup that I just described, work equally well. They're totally equivalent and will yield the same results. Categorical cross-entropy and using softmax on as the activation function for the output layer are just a common approach for when you have more than two classes. So I like to continue using that approach even when I only have two classes, just because it's general and it's the case that we're going to use whenever there's more than two classes anyway. So I just like to stick with using the same type of setup even when we only have two outputs. All right, so after compiling our model, we can now train it using model.fit, which we should be very familiar with up to this point. So to the fit function, we are first specifying our training data, which is stored in train batches. And then we specify our validation data, which is stored in valid batches. Recall, this is a different way of creating validation data, as we spoke about in an earlier episode. We're not using validation split here because we've actually created a validation set separately ourselves before fitting the model. So we are specifying that separated set here as the validation data parameter. And then we are setting our epochs equal to 10, so we're only going to train for 10 runs this time, and setting verbose equal to 2 so that we can see the most verbose output during training. And one other thing to mention is that you will see here that we are specifying X just as we have in the past, but we are not specifying Y, which is our target data usually. And that's because when data is stored as a generator, as we have here, the generator itself actually contains the corresponding labels. So we do not need to specify them separately whenever we call fit, because they're actually contained within the generator itself. So let's go ahead and run this now. All right, so the model just finished training. So let's check out the results. Before we do, just if you get this warning, it appears from the research I've done to be a bug within TensorFlow that's supposed to be fixed in the next release, actually, is what I read. So you can just safely ignore this warning. It has no impact on our training. But if we scroll down and look at these results, then we can see that by our 10th epoch, our accuracy on our training set has reached 100%. So that is great. But our validation accuracy is here at 69%, so not so great. We definitely see that we have some overfitting going on here. So if this was a model that we really cared about and that we really wanted to use and be able to deploy to production, then in this scenario, we would need to stop what we're doing and combat this overfitting problem before going further. But what we are going to do is that we'll be seeing in an upcoming episode how we can use a pre-trained model to perform really well on this data, and that'll get us exposed to the concept of fine-tuning. Before we do that, though, we are going to see in the next episode how this model holds up to inference at predicting on images in our test set. By the way, we are currently in Vietnam filming this episode. If you didn't know, we also have a vlog channel where we document our travels and share a little bit more about ourselves. So check that out at DEEPLIZARD Vlog on YouTube. Also, be sure to check out the corresponding blog for this episode, along with other resources available on DEEPLIZARD.com. And check out the DEEPLIZARD HIVEMIND, where you can gain exclusive access to perks and rewards. Thanks for contributing to collective intelligence. I'll see you next time.